Okay, what I'm going to start off with is the introduction to burst and background estimates, and just so that we understand what we're talking about when we talk about leakage. In most reticulation systems, we've got two main forms of leakage. We've got burst leakage and we've got background leakage. And it's quite important to differentiate between the two different forms of leakage because they both require a different approach when you're trying to deal with them. A typical burst is, all of you have seen leaks like this regularly. They end up in the newspapers. This is a typical burst leakage, typical burst pipe. This particular one is running at about 70 meters of pressure. This one is a mains burst, a very large mains burst, also running at between 70 and 100 meters of pressure. This is a bulk distribution main leak, which was running at probably 200 meters of pressure when it burst. And you can see it was fairly substantial. So all of these huge leaks that you see are termed burst leaks. Sometimes they can cause enormous damage. Johannesburg, or a suburb that was inundated when a large mains burst occurred a number of years ago, and it flooded the whole township. It basically washed cars off roads and was headline news for a couple of days. However, we then have background leakage, and in this particular case you can see a tiny leak here that is occurring from a pipe in a system, and most people would not really worry about background leakage. However, what the United Kingdom water authorities did back in the 90s, they created a task force where all the water companies put their top professionals together in order to come up with a methodology to address leakage in major water supply systems. And they developed an approach called the BABE approach, which stands for Burst and Background Estimate methodology. And it addresses leakage in the form of bursts, which are the big leaks that we've seen, and then background leaks, which are the sum of all the tiny leaks in the system. Now, it's important to understand every network will leak. You cannot get rid of leakage. You can find burst leakage using normal leak detection methods such as sounding, correlation, etc. You cannot find background leakage because it's so small and the equipment won't pick up the noise from a typical background leak. However, background leakage can often be so significant that it's greater than the burst leakage. So it's important to understand every system will have leaks. Some of them will be burst leaks that you can find with leak detection equipment. Others will be background leaks that you can only repair through replacing the network or through pressure management. Now, what the UK did in order to address leakage in a normal water supply system, they came up with a standard methodology called the BABE methodology. And the BABE methodology has 4 pillars. The first one is logging and analysis of minimum night flows. So basically you're looking at the water going into an area between midnight and say 4 o'clock in the morning and trying to identify how much water goes into that area during that period of minimum night flow, and then establish how much of that water is legitimate use and the balance is then leakage of one sort or another. We're not going to discuss that today, but that is one of the pillars. The second pillar is water auditing, where you carry out a water balance of an area, and by doing so you differentiate between the losses and the revenue water. You can then split the losses into physical leakage and commercial losses. So there's two different types of losses or in your system, and we will be talking principally on physical leakage today. We won't go into the apparent losses, or they're often referred to as commercial losses. A third element is the economics of leakage, and they came up with economic level of leakage, etc., various buzzwords and terminology. Basically, what you're looking at here is how often should you go into an area to find leaks that have not been reported. And in many cases, it's not viable to do that even in the first place. If you're not repairing the visible leaks and the leaks that have already been reported, there really isn't a lot of sense in spending money going out looking for leaks that haven't been reported when you're not fixing the ones that have been reported. So there's a whole economics of active leakage control, and that's a third element of the BABE methodology. The fourth element is pressure management, and that's the one we're going to talk about this afternoon, and hopefully you'll get, this is basically, if we finish the presentation here, this slide basically sums it up in total. If you go away with one takeaway today, it's that pressure management is by far the low-hanging fruit of low-hanging fruits in the quest to reduce leakage in a water supply system. The paybacks on pressure management can vary, typically from the 400 or 500 installations that we've designed and built. Typically anything from a month to 2 years would be your payback from a pressure management installation. And generally we are in the 3 months to 6 months range, but it can be as low as a month, it can be as high as 2 years. If you compare that to pipe replacement typically has a payback 7 years up to 30 years, depending on the cost of your material, the size of the pipes. So pressure management is without question one of the most, well, without question, it is the most cost-effective intervention to save water that you can consider in most systems. It will not always work. I'm not saying it's the silver bullet for leakage in a system, but where it works, it will often give you spectacular results, and at the very least, it will prolong the life of your reticulation system, which, if you work out the value of that, you'll often find that extending the life of your system by 5 or 10 years has a far higher value than the water that you're saving. And it's generally not taken into account in the financial model. Okay, when we talk of pressure, there's no way just about every pressure presentation worldwide uses a couple of pictures from a gentleman from Canada by the name of Ken Brothers, who was one of the first chairman of the IWA, International Water Association's water loss management teams, the water loss team. Ken took a couple of pictures just to demonstrate what we mean when we're talking about pressure and leakage. Basically, pressure drives leakage. This is a pipe that's leaking at low pressure, and this is the same pipe leaking at high pressure. It's fairly obvious what we're trying to present here. I don't think we need to dwell on that one too long. what we've got here is a typical system. This is if you imagine a small suburb or 1,000 properties up to 10 or 20,000 properties, it's being supplied from a water tank or a water reservoir, an elevated tower. The pressure in the tower is perhaps 100 meters. You would typically have a PRV in here. The PRV would give you a stable pressure of 60 meters into the zone, and during the daytime at the critical point, due to people using water, you have friction losses which will give you, say, 20 meters at the critical point. Okay. At night time, when people are asleep, very few people are using water. So the main use for the water are a few people flushing toilets or having showers at night, as well as the leakage in the system. And instead of friction loss that we had previously of 40 meters, we might only have a friction loss here of 5 meters, which means that the pressure at your critical point increases to 55 meters, and that will cause a leak in the system. So typically, most burst pipes in a reticulation system will tend to occur between midnight and 6 o'clock in the morning, when the demand for water is very low, and as such, the static pressure in the system has increased. Very basic. We've managed to create a cartoon of this. Obviously, I should probably be working for Disney, but anyway. So basically, you've got a system here where you've got high pressure at the water tower. During the daytime, you can see the water pressure. We have the red line here represents the friction loss. At night time, that friction loss reduces, and the pressure at the critical point will increase, which hopefully you can see here. And once it increases at night time, then you get the leak developing. Obviously, no expense has been spared on this slide, as you can appreciate. So we'll move on to the next one. With pressure, there's two key things I'm going to talk about here, just to give you the background to this. New burst pipes. If you were to reduce the pressure, if you were to reduce the maximum pressure that a zone experiences at night time from 100 meters perhaps to 50 meters, so you reduce it by a factor of 2, you will reduce the number of burst pipes in that system by approximately 8. So by reducing the maximum pressure, so that's your nighttime pressure, by 50%, you drop it from 100 to 50, you can reduce the number of leaks in your system to by a factor of 8. So that's when it comes to new burst pipes, that is the impact of pressure management on new burst pipes. Now, to discuss, so that you understand, we've talked previously about burst and background leakage. We now have to take into account not only the burst pipe leakage, but the background leakage that occurs with the bursts. And there was a methodology called the fixed area variable area discharge theory. It's a bit of a mouthful, and it was given an acronym by Alan Lambert and John May in the 1990s. The acronym is called FAVAD. It stands, as I mentioned, fixed area variable area discharges. And this is an explanation to try and explain why the leakage in some zones is more sensitive to pressure than other zones. And the reason for it is mainly the pipe material and the type of leak that occurs on certain pipe materials. To explain this, if you have metal pipes, typically a metal pipe will end up with corrosion holes, which are small circular holes in the pipe. The size of that hole does not change during the day or night with pressure. The hole stays the same size. However, if you have asbestos cement pipes and plastic pipes, typically the leaks on those pipes occurs through the joints or cracks on the actual pipe. And as the pressure increases, the crack will open up. And so on plastic and asbestos cement pipes, you have variable area discharges, and on steel, iron type pipes, you have fixed area discharges. And what that means in real life, is if you have pressure of 50 meters or 100 meters, if you change the pressure from 50 meters to 100 meters on a steel pipe system, the leakage will increase from 1 to about 1.41, which is a 40% increase. So you double the pressure and you increase the leakage by only 40%. So that's not too significant. On a plastic pipe system, however, if you double the pressure, you will increase the leakage from 1 to almost 3. So that's basically a 300% increase, 3 times what it was. And that is the impact of variable area discharges. And what it means is plastic pipe systems are very sensitive to pressure. The leakage from a plastic system is more sensitive to pressure than leakage from a metal pipe system. If you have a mixture of plastic and steel, or plastic and metal, or you don't really know what's going on in the system, you can generally budget on doubling the pressure will double the leakage. And conversely, if you can half the pressure, you will half the leakage. So leakage drives pressure drives leakage, and anything you can do to reduce the pressure will reduce the leakage. Okay, so what can we do? How can we reduce pressure in a system? One of the easiest things you can do is to drop in an orifice plate into the network, and it will reduce the pressure. It's basically putting a constriction into your pipeline. It can work if you've got very high pressures and you want to reduce it. This is by far the cheapest and quickest way of doing it. You really don't have any control over the result, however, and a more common approach, and one which we don't recommend at all, is to use a gate valve where you throttle the valve. This is often used to reduce pressure in systems by operators within the water companies. It is not advisable. Gate valves were designed to be either fully open or fully closed. In order to reduce the pressure, you have to almost close the valve, so there's only a small amount of area open, and as a result of that, it typically cavitates and causes leakage, and that's not what you want. You will if you use a gate valve to throttle pressure, you will invariably destroy the seat in the valve, you will get cavitation, you will end up destroying your valve. They are not designed to control pressure. Pressure reducing valves are designed to control pressure, and they come in a variety of colors. You can get green ones and red ones and blue ones. Most of them are, if you buy a high quality valve, you will normally not go wrong. It's not the sort of valve that you try and skimp on. It's going to be in the ground for 50 years to 100 years. So you do want to buy a high quality one, and you can normally tell the high quality ones from the low quality ones by the price. So unfortunately you have to dig into your pocket and buy a decent one at the start to give you 50 or 100 years of life. There's a whole bunch of valves that we're not tied to any particular valve maker. There's a whole bunch of fairly good valves. You get the Durots, you get Burmats, you get clay valves, you get Baker. Oops, hang on. You get Baker valves. There's Singer valves. There's a whole bunch of fairly good quality valves. The manufacturers will generally claim that each valve is a silver bullet and it's got some sort of special feature, etc. In general, if you buy a decent valve, it will last you 50 to 100 years, and it will give you good service. So each valve has its benefits and disadvantages, but generally they all do roughly the same thing. Most of the valves have a thing called a pilot, and here's a picture of a pilot. It's about 6 inches, 8 inches long. Unfortunately, most of them are made of brass, which is good for the quality, or bronze. It makes them quite attractive for the scrap merchants, so you have to be a bit careful on sealing your installation in many countries, particularly where I work. You can't leave these things alone. Anything that's made of bronze or brass will disappear if it's not under a 5-ton block of concrete. So the trouble is, without the pilot, the valve is not operational. You get different pilots. Each company has its own pilots. We find the clay valve one, in our view, and I don't have shares with clay valve, the CRD pilot is one of the most popular. It's like the Land Cruiser of pilots in our business. It is made of, I think it's a brass pilot, and that's the one we use. Now, when you're using a pressure reducing valve with a pilot, you typically create a fixed outlet pressure going into the zone. So you have a zone of maybe 5,000 or 10,000 properties, and you have a fixed pressure going into that zone. The objective is that at your critical point, you get a pressure of roughly 20 meters, 25 meters at the maximum demand. So when the friction losses are highest, you should have 20 meters at your critical point. Now, the problem with that is, once you've designed a zone for that, most of the time your zone is not operating at full capacity, which means the friction losses are not at their maximum. They're actually somewhere between maximum and minimum, which means the pressure at your critical point most of the time is then above the 25 meters of pressure. And that's where other devices, controllers, electronic controllers, hydraulic controllers come into the picture. These are devices that you can attach to your pressure reducing valve, which will give you greater control over the pressure during the off-peak periods. And any pressure reduction that you can achieve will reduce leakage. And that's what it's all about. You get different types of controllers. And there's various types. You get time control, flow control, you get closed loop control, you get very fancy controllers now that have self-learning algorithms. They can make the tea, they can do whatever you want. It's important to realize every additional item that you add to your pressure reducing valve is an item that can break down or go wrong. It adds further complexity. So for every benefit you get, there is an associated disbenefit, either through maintenance and breakdowns. So it's always a balance trying to find appropriate technology. And in many cases, a standard pressure reducing valve with fixed outlet control is by far your best option. You only go for the more complicated forms of pressure control if you have the technical capacity to manage them and if it makes sense, financial sense as well as operational sense. So I won't dwell too much on the various issues of controller selection. I'm going to go on to explain to you how it works. This is a zone, this is a 24-hour profile, and don't worry, you don't need to get bogged down too much in the detail. The red line at the top represents the inlet pressure to the zone. The yellow line, which is just below the lead, represents the flow going into the zone. And the black line at the bottom, which is covering this grey area, this black line here, this black line there that you can see, that is the pressure at your critical point. So that's the point of lowest pressure in your system. And in this particular example, I have decided that we want 10 meters minimum. It's a bit low for most systems, but just bear with me on this one. It could be 20 meters, it doesn't really matter. The point is, at your critical point, you can see that even during the peak daily demand, you've got about 15 to 16 meters, and at night time, we're up to about 36 meters. So we've got excess pressure in the system. Anything we can do to reduce that excess pressure will reduce leakage. So I've shaded in the area of excess pressure. So that area is representing what we're trying to get rid of. Now, we're going to use a fixed outlet pressure reducing valve here. And a pressure reducing valve is simply, it'll give you a fixed pressure going into your zone, and it gives you a variable pressure at your critical point. Now, by using a fixed outlet pressure reducing valve, we drop the pressure in this case to about 38 meters, so that during the peak demand period, we're down at the 10 meters that we're looking for. So that's fantastic. We've taken a strip off that grey area. We now have a smaller grey area where we have some excess pressure at night time, and then again later in the day during the 24 hours in the morning. So you can see that the grey area has decreased simply by reducing the pressure through a fixed outlet pressure reducing valve. This gives you the maximum benefit from a single device, but we can still do better than that. We can now reduce it using a time controller, which involves setting a lower pressure during certain times of the day. So we use time control, and it's a box. It's simply a box with some solenoids in it, and we basically cut those peaks off at the critical point. And here we go, there's what it looks like. There's various different types of time controller. This is your simplest, most basic control. It is the cheapest form of pressure control. Whether it's cost effective, you need to decide for each zone. That's one being fixed up, it's a small one. And that takes off a bit of the peak in the morning, between 0 and 6 in the morning, and a bit in the afternoon peak. Okay, so we've managed using time control to take off a bit more of that grey area that we're trying to get rid of. If you've got more money to spend, and you want to do even better, you can go to flow control. Questions at the end. We'll do questions at the end. We can use flow modulating control, where we adjust the pressure according to the demand. And there's various types of controllers. I'm not going to go into the different types. That's what there's a couple of them that we look at. Using flow control, you can take the pressure off there. It's a fairly simple example, this, but you can see that by using a more complicated controller, you've taken off some of the excess pressure. Whether or not it's cost effective in the long term is debatable, and it varies from area to area. That's the question you need to decide. You can use closed loop control. That involves putting in a sensor at the critical point, sending back information to the controller, and then the controller will reset itself or adjust the pressure so that you get absolutely your 10 meters or 20 meters at the critical point. Now, oh, hang on, we'll just go back one here. What's important to realize here is by adding that device at the critical point, you now have another widget in the chain of events that can go wrong. So depending on how good your technical teams are and whether things are getting stolen, you may find that in certain cases the appropriate technology is the basic fixed outlet control. You can go for a number of different types of controller. You get hydraulic controllers. There's a couple of hydraulic controllers. Most valve manufacturers have their own hydraulic controllers. They're normally stainless steel, and if you've got a good technical person that knows what they're doing, they can make these things work very well. The problem is if that technical person isn't there when things go wrong, which they invariably will, then someone else will come along and disable it, take it out, or sell it for scrap. So you need to have good people in your team to manage this type of thing. So always bear that in mind. Training. Training of the technical personnel within the water utility is always a big item. My colleague Neil will probably touch on that in the next presentation. We have courses where people take the valves apart and put them together again. It's very important that the people operating the system have the technical knowledge to manage the pressure reducing valves. They are so important in a system. There is no point putting one in the ground and just ignoring it. It's like a car engine. If you don't service it regularly, it will stop working. Someone will disable it. Bits and pieces will disappear, and it's then useless. And then you've got full pressure going into your system. So they are very good devices when they're working, but they do need to be looked after. And they are extremely important in any water supply system. So there's a couple of pictures there. Chris mentioned earlier, for those of you that haven't seen it, we've done a few big installations. Kailicha was the first of the massive installations.
Ronnie, I'm just noting the time. We're at 4:15, which is the scheduled Q&A time. I can afford to give you 5 minutes for concluding remarks and takeaways, and then I want to invite the audience to engage. All right.
I did start a few minutes, 10 minutes late, Chris. Anyway, okay. That's fine, Chris.
Fair enough. We can if you've got 10 minutes left, I can give you that much time.
All right, good. 10 minutes, so I'll go through it in 10 minutes. Good. Okay, Chris. I'm just going to run through the 3 big installations just so you can see what they look like. Kailicha is one of the first of the big installations. That's it there with 3 valves. We used a manifold system to cut down on costs. It's much cheaper to have 3 small valves than 1 big valve. The savings were about 9 million cubes per annum. We dropped the average daily flow from 2,500 cubes an hour down to 1,500 cubes an hour. Quite significant. The hourly savings were basically an Olympic-sized swimming pool every 2 hours, which is worth quite a lot of money, obviously. The second one, which Neil actually designed the second one, which is why it's the Rolls-Royce installation that we've designed. It's a very nice installation. It's got 4 PRVs in it with the manifold at both ends. The third of the big guys was the Seba King Everton one. This is the one that we did as a performance-based contract where we paid for it with our own money and we operated it and maintained it for 5 years. The client paid from the savings, roughly 15% of whatever was saved over a 5-year period, and that paid for the installation. It was one of the bigger ones. Again, 500,000 people. Average pressures were about 30 to 60 meters. It had a night flow originally of 2,800 cubes an hour. That's the night flow. That's basically your leakage. That's what it looks like when we designed it and we built it. We had to cut in the big pipe, and we took the big pipe out and put some manifolds on, and then we slotted in the installation. This was all done within an 8-hour period, which was quite, we were going for the Guinness Book of Records on that one. The savings were about 8.5 million cubes per annum, which again is a small lake. There's the savings there, that shows the savings. And in rands or dollar terms, over 5 years, the savings came to about $20 million, or 152 million rands. The savings again were in the order of 1,000 cubes per hour, which is an Olympic-sized swimming pool every 2 hours. I've got my 5 minutes left, so I'm going to give you a little case study on fixed fee modulated pressure control. I've been talking about controllers and how it's great to use controllers and when you should use them. I just want to, we had a study called, down in South Africa, and this study, we had an inlet pressure, which is the blue line, and the critical point pressure, which is the red line. Now you'll notice that both of them are very high. They're up almost 80 meters of pressure. There's not a big difference. This particular zone was perhaps a bit over-designed, and the pressure going into it was certainly very high. We had a minimum night flow originally in the zone of about 158 cubic meters per hour, which had a minimum night flow divided by average daily flow of 60%. So it was a very high leakage zone. We put in a fixed outlet pressure reducing valve, and we set it initially at about 47 to 48 meters. So the red line represents the pressure going into the zone, and the blue line represents the inlet, the original pressure. So we dropped it from the blue line to the red line. So we've taken off about 40 meters of pressure. That dropped to minimum night flow from 150 down to about 48. So we basically took 2/3 of the leakage by simply reducing the pressure. The pressure at the critical point basically looked like this, which was about 38 meters. Now you could still take it down further. You could take it down probably to about 20 if you really wanted without having a riot on your hands. But anything below the 38, we were worried about getting complaints. The client didn't want complaints. So a lot of the time you kind of get a balance between complaints and high pressure. So we settled on 38 meters. What's important here is to look at that logging result. There is the difference between the day and the nighttime pressure at the critical point is minimal. In a case like this, there would be little point in putting in a controller to get extra advantage at certain times of the day. So this is a classic example where you would just use a fixed outlet control. Okay, and that's what that slide looks like. That was the before and after for the flow. And the final couple of slides, this is another slide, this is another zone, and this is a zone where you do have a significant difference between day and nighttime pressure at the critical point. And if we have a look here, this is the fixed outlet pressure at the critical point. You can see it varies from about 50 meters down to about 30 meters. You have scope here to control pressure at certain times of the day. So in this case, we may put in a pressure controller, and that is, unfortunately, it wasn't as successful as some of the other ones, but we did manage to reduce the variation to about between 5 and 10 meters at the critical point using a controller. So it's important, don't throw a controller into every zone. You can only, you have different types of controllers. There's self-learning types, there's hydraulic types, there's a whole bunch of controllers on the market just now that will do different things, and you can select which one is the most appropriate for your installation. And last slide, my very last slide. This is the first pressure reducing valve ever made. It was by a gentleman called James Watt from Glasgow, believe it or not. So I felt nostalgic, and I thought I would just throw that one in to point out that the Scots actually invented pressure management. So on that one, I'll finish. Thank you.
Ronnie, that's fantastic. Thank you so much. Mute you for a second. We do have a couple of Q&As from the audience. The first one is from an anonymous source, asking to please explain how to position a PRV. What factors do you consider and necessary steps when setting that location?
Hang on. Okay, to set up your pressure zones. It's a really good question, that one, and not one I can really answer within a couple of minutes. Generally, if you have a city or a whole area, you would normally try to carve up the area from the outside, moving towards the middle, so that you're looking to isolate an area that you can cut off with just 1 or 2 pipe cuts, and you shouldn't have to have 20. You shouldn't be cutting 20 pipes to create a pressure zone. You would normally, it's a bit like what they say about eating an elephant. You start from the outside and just small chunks and moving inwards. It's a very it normally follows the topography. It normally follows things like roads and rivers and such like. So we do there's a whole training session on creating pressure management zones, which we can maybe present through Rock Blue at some point in the future. So I can't give you a really easy answer. That's a hellish question, that one. Anyway, that's the best I can do in a couple of minutes.
Yeah. Thank you, Ronnie. A couple of points I just want to raise. My tech team tells me that participants can use the hand raise function at the bottom of the screen if they want to be called upon and ask a audible question. We'll enable your microphone to do so. But please use the Q&A chat function. It's more efficient. There have been a couple of questions that I want to respond to. We are recording this session, and we are looking at how best to make it available. Once we've done that, we will send an email to the participants, letting them know where that can be accessed. Our next question for Ronnie is a question whether the nature of soil conditions can cause leakages.
Definitely, absolutely. You will often find that during especially in areas that have got clay. The clay will move, and you will often find that during the dry season it will shrink a bit, and during the wet season it will expand, and that type of movement will create problems in any reticulation system. It will cause pipes to burst. Any movement at all will cause the pipes to burst, whether it's traffic movement or trains, railways, anything like that, and soil conditions certainly. So changing soil conditions, moisture conditions in the soil will certainly cause movement, which in turn will result in pipes cracking or leaking.
And finally, if there's a question from the floor that to assist with the formula, or is there a formula for determining the water loss using the minimum night flow measurement?
Yes, the minimum night flow, I didn't go into that in detail. Basically, the minimum night flow can be calculated based on the population. You can work out roughly, if you know how many people are in a zone, you can calculate, there's guidelines on how many of those people would typically flush the toilet during any 1 hour. So that gives you the typical toilet use during the hour of minimum night flow. You then can make an estimate of the background leakage that you would expect from that zone based on the pressure, the length of mains, the number of connections, and the number of properties. So there's a guideline on that, and then you add those two together, and that gives you your expected minimum night flow. You then compare it to your measured minimum night flow, and if the two numbers are reasonably close together, then you know that you don't have a major burst problem. If the two numbers are quite far apart, that gives you an indication that you do have a burst problem in that zone. And the minimum night flow is, in my view, one of the most important factors that you can look at when managing leakage in a zone. It is by far the best indicator of leakage in a zone. And it's good to be able to get an estimate of what you would expect so that you can determine whether or not you have a problem and how big that problem is. So it's a very good indicator, and it deserves a lecture on its own.
A final question, Ronnie, while we still have some time. A very general one. What are the most common or egregious mistakes that utilities make when engaging in pressure management?
Sure, that's a tricky one. I would say that not managing their boundary valves on a regular basis is, in my view, the biggest oversight of a water utility. Our biggest problem when it comes to pressure management is finding that the zones have been breached, either due to operation and maintenance issues, or there's been a burst pipe and they've had to connect to two zones, and then after repairing it, they haven't bothered to shut them off again. And you end up breaching the zone, in which case all your best pressure management experience, all the controllers, even the smartest controller, cannot handle sort of a plumber going round and opening a zone valve. That is by far the biggest problem that we face, is not managing the zone valves, keeping those that should be closed, closed, and keeping those in the middle of the zone that should be open, open. As soon as you shut valves in the middle of a zone in order to fight a fire or to fix a leak, you've got to open them all again, or the zone does not operate as it was originally intended. And that is the biggest problem by far that we experience everywhere in the world. First world, third world, developing, undeveloped. It's the same problem everywhere.